so now we start the diffraction, right? So this is the diffraction. What is the diffraction, Sanjay? You tell me what is the diffraction? Diffraction is nothing but, you told me, correct, the bending of light. Bending of light around, right, around the corner or obstacle in the path of light, Is it clear or not? The diffraction. What is the diffraction? Listen one thing. Suppose the light is coming, all right, and you placed a coin of the obstacle like this. When you will see, it is not like that. If you place the screen in front of this, it is not like this, that you are getting the light only this portion. Rather, when the light wave reaches, so they are producing the diffraction. They are bending around the corner. And this thing is called the diffraction, right? This thing is called the diffraction. So not only here, you will get the light at this portion also, but the light intensity will be less over here. You will get the light here also. LIGHT, light here. Are you getting or not? For example, if you consider this the tube light, if I put my hand, you will get the light just behind my hand also. Why? Because when the light rays are coming, so they are bending around the corner of my hand. So therefore the light is also reaching over there. For example, in your house, if the light of the kitchen is switch on and all other lights are switch off, you will get the intensity of the light in your other portion of the home also, but the intensity will be less. Did you observe this or not? All the light travel in the straight line. If the light is traveling in the straight line, so here the complete shadow will be formed, but it is not so. The shadow is very less intensity, and you will get the less intensity light in behind of this obstacle or in the path of the light. Do you understand or not? So that is why if you switch on the light in your kitchen, so the other parts of the house is also brightening, giving the intensity of the light. Are you getting or not? This is called the diffraction. One more thing, not only like this, if you make a hole in this cardboard, are you getting or not? Since we know that light is always traveling in the straight line, so if you put a screen over here, are you getting or not? So if light is only traveling in the straight line, right? So what you should have? You should get the light on in this small portion only, because the light is coming like this, right? But when an aperture comes and corner of aperture, bending of light around the corner or obstacle in the path of light, or due to or bending due to the aperture. If aperture is also there, the light will bend like this, like this, like this, like this, like this. So not only here, you will get the light in this portion. Is it clear or not? Is it clear, Sanjay, or not? Why it is so? Why it is so? Can you give the answer? Why it is so? Why it is diffracted? Listen, if this is the slit or this is the aperture you are assuming, when the light which is over there in front of wavefront, correct, Sanjay? So according to the Huygens principle, every particle present on this wavefront act as a new source of light. So therefore, from here, the spherical wavefront emerging out in each direction. Are you getting or not? So therefore, when you will see the screen over here, so the light is not only found in this region, whether the light is found everywhere. Do you understand or not, Sanjay? So this is explained on the basis of the Huygens principle. H-U-Y, Huygens principle. Is it clear or not, you tell? Right? So this phenomena is called the diffraction. Right? Copy this. Okay, so this is called the diffraction when the obstacle or the aperture comes. This is the obstacle, and this is the aperture. Right, comes in the path of the light. The condition to get the diffraction, condition for diffraction, right? What is the condition for the diffraction? Listen one thing. To get the diffraction, the size of slit, size of aperture, size of slit or aperture or obstacle must be nearly equal to the wavelength of the light, wavelength of light. Do you understand this? This is the condition. Otherwise, the diffraction you will not get. What is the condition? The size of the aperture or the slit must be approximately equal to the wavelength. What is the size? If this is the obstacle, the size of this obstacle is A, the size of this aperture is A. So if the wavelength is this, so wavelength will be approximately equal to the size. Then you will get the diffraction only, otherwise you will not get the diffraction. Understood? Yes, copy this. So this is the diffraction. The diffraction may be considered of two types, right? So now you can consider the diffraction of two types. Two types of diffraction. Two types of diffraction. Is it clear or not? Two types of the diffraction. What are the two types of the diffraction? First is Fresnel diffraction. Fresnel diffraction. What is the Fresnel diffraction? Do you have idea, Sanjay? What is the Fresnel diffraction? If this is the slit and this is the screen, right? This is slit, the screen, right? And this is the source of the light. Source of the light. So when the source of the light is producing the light, it acts as a new source of light. So the light travel in this way also. And here you will get the diffraction pattern on this screen. Is it clear or not, Sanjay? Like this. Right. So if this distance is d and suppose this is the distance d, listen. From the slit, the source is at finite distance. And from the source, from the slit, the screen is at also the finite distance. Then the diffraction produced on the screen is called the Fresnel diffraction. I am writing the definition. Right, it is very important. Sometimes it is asked if source and screen are placed at some finite distance from slit, the diffraction, then the diffraction pattern, produced on screen is called, what is it called? Fresnel diffraction. Fresnel diffraction. Right. The study of this type of diffraction is very tough, so we will not do this. Study of this diffraction, pattern is, study of this diffraction pattern is very tough. Very tough mean out of syllabus, you can say. We are not going to discuss this. Right? We are not going to discuss this. But this is the definition of the Fresnel diffraction. When the screen and the slits are, when the screen and the source are at some finite distance from the slit, then this diffraction pattern, which is very tough in study, and we are not going to discuss this. Okay, copy this. So the next type of the diffraction is the Fraunhofer diffraction. Fraunhofer diffraction. right? Fraunhofer diffraction. What is the Fraunhofer diffraction? When the source, the screen, or either of this, when source or screen, source and screen are placed at very long distance, then diffraction produced is Fraunhofer diffraction. F-R-O-U-N. Fraunhofer diffraction. Is it clear or not? And we can discuss this. Are you getting or not? So, for example, the single slit diffraction. Right? Copy that. So, in the single slit diffraction, the source must be at infinity. What does it mean? If this is the slit and this is the screen, suppose. So, the source must be at infinite. What is the meaning of the infinite? The light from the infinite source are reaching in the form of the plane wavefront. Is it clear or not? Tell me. So, but it is not possible to keep the source at very long distance. So, to produce this wavefront, so that it should reach parallelly to this slit. So, what we have to do? Suppose this is the source of light, and you take a lens and put this source on the focus of this lens. So, what will happen then? The light's rays are coming like this, and they become parallel to the axis. So, although the source is at some distance, at finite distance, but the wavelength or the wave, the light wave reaching on this slit is right in the form of the plane wavefront. So, it looks like that the light is coming from infinite distance. Is it clear or not? In the same way, we cannot place this screen at very long distance. It is not possible. To get the diffraction pattern again, we have to put a lens in front of the slit. So, when the light wave are coming, so they will, right, due to the diffraction, they will produce the diffraction pattern on this screen. Is it clear or not? So, either the lens, this is L1 and L2, so we can put the two lenses in front of the slit, behind the slit, to get the Fraunhofer type of the diffraction. Is it clear or not, Sanjay? Copy this. Do you understand this? There are the two types of the diffraction, Fresnel diffraction and the Fraunhofer diffraction. Is it clear? Right. Okay. Now diffraction of single slit. So the Fraunhofer diffraction we are going to discuss. It is in our syllabus, and the diffraction by the single slit we have to discuss also. The diffraction due to the circular aperture. You may write diffraction due to circular aperture is also there. Circular aperture. Right. So now first I will discuss what is that. The diffraction due to single slit diffraction. Single slit diffraction. Alright. Single slit diffraction. What is the single slit diffraction? In the YDSC, you have seen this is the YDSC. Don't make this first. There are the two slits. Alright. And here the maxima, minima you get. I told you. Do you understand or not? So this is the YDSC, Young double slit experiment you are getting. But if I consider only the one slit, so I close this slit. So what type of the fringe pattern you will get on this screen is called the single slit diffraction. I am taking only the one slit, and the size of the slit is A, and the light is coming right from the infinite in the parallel. Are you getting or not? Like this, right? So when it reaches, this wavefront are reaching on this slit. So according to Huygens principle, every point act as a new source of light, and these new source of light produce the spherical wavefront in all directions. So, in the screen, which is placed at distance d at the site A, is it clear or not? So, in the center, you will get the very high intensity, and this is called the maximum. And either side of this, you will get the minima, right? And then the maxima. But the maxima, the second maxima, right? This is the secondary maxima is of less intensity. Then again the minima, then again the maxima, minima like this. Are you getting or not? On this side also, this is the minima, right? Then the maxima, minima, and the. Do you understand, beta? Sanjay? Are you getting, Sanjay? Right. So here the maximum light, the intensity is very high, right? Then the intensity reduces, then the intensity reduces. Is it clear or not? On this side also, the intensity is reduces, then again the intensity. Is it clear? This is called the central maxima, right? And this is the first D1, D2, D3. This is D1, D2, D3. Is it clear or not? Here the maximum intensity is I naught. The intensity is reduced to I naught by 22, and then further it is decreased by 61. Right. So as we are moving, the intensity is decreasing. While in the YDSC, if you remember, the intensity is what? Similar of all the fringes. For all the fringes, the intensity was similar, but in this case, the intensity continuously decreasing, and most of the light is in the central maximum. Is it clear or not, Sanjay? Copy this first. So I am writing a small theory, right? According to Huygens, right? According to Huygens, every point present on wavefront reaching to the slit acts as a new source of light. Act as a new source, right? And they produce the produced diffraction pattern, right? They produce the diffraction pattern on the screen. They produce the diffraction pattern on this. All right. In which on the center of screen, central bright fringe, central maxima, right? Central maxima is formed of large width, Is it clear or not? Central maxima. This is called the central maxima. Most of the light is in between in this central maxima only, right? And both side of this both side of this, the dark and bright fringe, dark and bright fringes of reducing intensity are formed. Is it clear or not? Which are called secondary maxima or secondary minima. Not only the maxima minima we will call in this diffraction, rather the secondary maxima or secondary minima we will call. Listen one thing, this is the first secondary minima, this is second secondary minima. Are you getting or not? And what is this? This is the B1. This is first secondary maxima. Is it clear? This is B2, secondary maxima. Is it clear or not? And this is the central maximum, whose width is W, which is the maximum as compared to other secondary maxima or minima. And the intensity is continuously reducing. I naught by 22, I naught by 61, you will remember. Right? Copy this. So now we will do some calculation. The first calculation is the width of, central maximum. Do you understand or not? Width of central maximum. Listen one thing. Every point on the slit act as a new source of light. If we consider this is the central maximum, this is the D1. So if you consider the one wave from this is reaching at this point and the other wave is reaching on this point, right? So these are the S1, S2 and number of sources are there. This is the distance A, suppose. Are you getting or not? So if this is the point, can you tell me what will be the path difference if it is theta? Yes. The path, this delta x, not path difference, I am telling this is the delta x is what? Say A sine theta. Are you getting or not? The condition for first D1, first secondary minimum. What is the condition for first secondary minimum? The path difference. What is the path difference? Delta x, A sine theta. Delta x must be equal to what? Can you tell? No. I am asking only for the D1. What? Repeat. Right. Very good. But in case of diffraction, this path difference is lambda. You have to remember. And why it is so, I will explain. This is the condition for the constructive interference. What should be the path difference? Lambda 2, lambda 3, lambda. But here, for the destructive interference, here the path difference for D1 must be equal to lambda. For D2, the path difference must be equal to 2 lambda, right? For nth secondary minima. Yes, tell me. The path difference must be equal to n lambda. I will explain this. Right? Copy this first. This is just opposite to the condition we found in the previous theory, right? right? Wait for 1 minute. Okay, so this is the condition for the nth minima, right? I'm just removing this. So, but we have to find this distance. This is the width of the central maximum. So, for this case, right, the delta x must be equal to what? Lambda is equal to a sin theta must be equal to what? Lambda. And if this is the theta, suppose, so if this is theta, this is capital D, this is capital D, and this is the theta again. So if I assume this is the y, a sin theta is equal to tan theta is equal to lambda, y upon d is equal to lambda, y is equal to what? D lambda over a. So what is the width? You tell. Width of central maxima. Central maxima. What is the width of the central maxima? W is equal to into y is equal to 2d lambda. Is it clear or not? So this is the main portion of the diffraction pattern, Fraunhofer diffraction pattern. This is the width 2d lambda over, because maximum light coming out from the slit is only contained in this region. So that is why the width of the central maximum formula is found, and it will be used in many questions, right? Copy this. So width depends upon the wavelength, the distance between the slit and the screen, right, and the wavelength and the size of the slit. Are you getting or not? So width is inversely proportional to A, right? So this is the width of the central maxima. If we want to find the position of nth dark fringe of the nth secondary minima, for that A sin delta x for position of nth secondary minima, nth secondary minima. How to find? This path difference must be equal to n lambda, right? And this is a sin theta is equal to n lambda, a tan theta is equal to n lambda, y upon d is equal to n lambda, y is equal to n d lambda over a. Is it clear or not? If this is the slit, this is the central maxima, this is D1, this is D2 in the same way. This is D3 and this is the DA. So this distance is n d lambda. Is it clear or not, Sanjay? Copy this. Right? Yes. Okay. Now we will find the condition for the maxima, secondary maxima. Are you getting? Right. Condition for secondary maxima, or you may write the position of secondary maxima. Are you getting? So if you consider this is the central maxima, right? This is D1, right? Suppose this is the D1, this is B1, this is D2, this is B2. So at this point, what is the path difference? Say lambda. If you move here, the path difference will increase or decrease? The path difference over here is what? Say lambda for the secondary minima, first secondary minima. Are you getting or not? So here the path difference will be greater than lambda or not? Greater than, right? And the path difference must be equal to for B1. What is the B1? First secondary maxima. It is the nomenclature. first secondary maxima. It is not fringe. It is the first second difference must be equal to what? Say 3 lambda plus lambda, more lambda by 2, then more lambda by 2, then more lambda by 2. The lambda by 2 will be added. If it is lambda, then lambda by 2, it is 3 lambda by 2, then it will be the delta x over here. It will be 2 lambda. The delta x over here, say 5 by 2 lambda. Lambda by 2 will be added. Is it clear, Sanjay? So you tell me, for B2, what is the path difference? For Bn, what is the path difference? You tell, Sanjay. 2n plus 1 lambda. Is it clear or not? And this path difference, if this is A, this is theta, and this is again theta, this is y, this is d. So I will write it is A sin theta, 2n plus 1 lambda by 10 theta, and A y upon d. Are you getting? So, what is the, I am writing this side, yn 2n plus 1 d lambda over 2. Is it clear? D lambda over 2a. Right? So, this is the position of nth secondary maxima. Nth secondary maxima from the center. That's it. Sanjay, you are getting this thing? Copy this.